Welcome to this next video in the playlist on complex analysis. In this video we're going to further discuss complex differentiation. In particular we're going to compare the complex derivative to the Jacobian matrix from vector calculus. So in previous videos where we've been discussing complex differentiation, I've done my best to impress upon you the difference between a complex derivative and partial derivatives and directional derivatives from vector calculus. However, we have not actually been comparing the complex derivative to its worthy equivalent in vector calculus, and that is what we're going to finally do in this video. We're going to compare it to the Jacobian matrix, which is actually its worthy comparison in vector calculus. So let's see what I mean by this. So let's just go over again something that we looked at in the previous video in this playlist, in particular the video entitled The Product and Chain Rule, where we discussed an intuitive understanding of the complex derivative, which we then used to derive the product and chain rule for complex analysis. So let's say then that we have a function f, which is a complex function from the complex plane to the complex plane, and as always we'll draw a picture for f, so we'll have our domain here and our codomain here, and it's essential that we go over this intuitive understanding because it's the same intuitive understanding that we use in vector analysis for what the derivative truly means, and indeed more broadly in all different forms of analysis. This is the better intuitive concept of what the derivative means, rather than viewing it as a gradient, which really only you can do in single real variable calculus and basic multivariable calculus. Engineering maths, you can view the derivative as a gradient. Anything higher up, and you have to have a different intuitive understanding of what the derivative is. So we have our domain and our codomain, and we're studying some arbitrary point z here, which is going to be mapped onto a point in the codomain over here, which is going to be f of z by our function f. So we saw in the previous video how the intuitive understanding of the derivative is that it is the ratio between the change in the codomain and the change in the domain. So let me have a look at this again. So if you make a very small change in the domain, which we'll call h, so an incremental complex number change in our domain, which is the complex plane over here, so h is some tiny little complex number, and we've drawn the vector that is the translation produced by that tiny little complex number. So you move therefore to a point z plus h, then of course that point is going to be some other point in the, going to be mapped onto some other point in the codomain over here, f of z plus h, and we're wondering about what this difference in the codomain is, what this tiny little difference in the codomain between f of z plus h and f of h is, i.e. the change in the codomain produced by our change in the domain. Well, the intuitive understanding that we should have of the derivative is that this difference, so f of z plus h minus f of z, so that is the tiny little complex number blue here. So you take f of z plus h, you take away what it was originally, that's going to give us that tiny little difference between them, which is a complex number, i.e. the change in the codomain here. Then our intuitive understanding of the derivative is that it is the ratio between the change in the domain and the change in the codomain. So you multiply the change that you had in the domain, which is h, by the derivative of the function evaluated at the point z. Now, if h is some macroscopic complex number, then this is only an approximation, and it may be a very bad approximation, but as you make h smaller and smaller and smaller and smaller and smaller, this converges on being true. So if we imagine that h is an incremental complex number, an infinitesimal complex number, then we can imagine that this relationship truly is true, and that is our intuitive understanding of the derivative, that it is how much you have to multiply any change that you make in the domain by to get the change that you produce in the codomain. under the function. That's the intuitive understanding that you should have of the derivative in this higher level maths, where you can't view it as being a gradient. And of course, this understanding, this works in all the different settings where we have derivatives. So if you think about single real variable calculus, you can imagine that as just being a function from the real line. So get rid of all the imaginary parts. Just imagine we have the real line being mapped onto the real line by a real valued function of a real variable here. The derivative means, you can view the derivative as meaning this equivalent thing back there, i.e. the ratio between the change in the codomain and the change in the domain, delta y over delta x. That ratio between change in y and change in x, that's what the derivative truly means. And it happens that when you have a graphical representation of the function, that is the gradient of the graph at that point. So there's our intuitive understanding of the derivative, and think about what this truly means. For every point in our domain here, there is a fixed value of the derivative of this function. This is just some complex number, so every point in this plane has a derivative at it for our function f. So every point has an ascribed complex number, and that truly what that means is, of course, we could imagine having incremental complex numbers in every single direction. So just drawing this on here, you can go in whatever direction you like, and if you want to know what each one of those little complex numbers goes to in the codomain here, what its equivalent change is over in the codomain, all you have to do is multiply it by the derivative at that point that we were looking at. Now think about that. This is just some complex number, so just to make it concrete, let's say it might be 2 plus 2i. When we multiply by a complex number, what is the intuitive understanding of that? It means multiply it or stretch out the vector intuition for the complex number. You know, we always think of complex numbers as having a little arrow associated with them, the translation produced by by adding that complex number. So you can imagine stretching that arrow out by the modulus of the complex number and rotating it by the argument of the complex number. That's what intuitively our understanding of multiplying by a complex number is. So if we think about the argument of this complex number, it is 2 plus 2i, so its argument is 45 degrees, so pi by 4 radians, and its modulus is going to be 2 squared plus 2 squared, which is 8. The square root of that, using Pythagoras' theorem, is 2 root 2. So we're going to stretch everything out by 2 root 2 and rotate it round by pi by 4. So therefore you can get an intuitive understanding of what it's going to do to all these vectors. It's going to rotate them all around by 45 degrees, so by about that much there. So that's representing pi by 4 radians. And then it's going to stretch them all out as well by a factor of 2 root 2. And that's what they're all going to become over here in the codomain. So if you imagine this one down here, that's roughly about 45 degrees difference from this one that I've drawn on here. So this one we can imagine is going to be mapped onto this one up here. So in fact, actually, what I drew here initially, because of course initially I was saying that this one goes to this one, if the derivative truly was 2 plus 2i, that wouldn't be correct, because obviously this hasn't been rotated around 45 degrees. This one would be mapped onto, so let me just do it in a different colour. So if we're studying our original one here, it would actually be being mapped onto something maybe like that, and therefore the point z plus h should have really been that point there. But I should have made this number different. I should have made it just a real number. I should have made it maybe just 1.5 would have been a good number maybe to have as the derivative there, because it looks as though I had just stretched it out by about 1.5. But that's the intuitive understanding of what the derivative means. It's the ratio between the change in the codomain and the change in the domain. And in the terms of complex derivatives, we are rotating all the little changes in the domain round by argument equal to the derivative at that point, and stretching them all out by the modulus of the derivative at that point. And that understanding, this is crucial, because this understanding of the derivative is what we can take up to all higher levels of maths, where you can no longer intuitively view the derivative as a gradient, and you can use it even in the more simple parts of maths, i.e. real calculus and basic multivariable calculus. It still works as an intuition there, This is the master intuition for what the derivative means. Remember, of course, that if h is not infinitesimal, it's only an approximation, this relationship. It converges on being true as h converges on being 0. And it may be a very bad approximation. If you made h something enormous, it would potentially be a very bad approximation, depending on the complex function in question. Right, so that was just reviewing what we've already been through. What we now want to do is compare this to the equivalent concept in vector analysis, and this concept of the derivative, i.e. the ratio between the change in the codomain and the change in the domain, this is a concept that goes over into vector analysis, and there is the equivalent concept there for a true derivative, and that is the Jacobian matrix. So we'll have a break here, and in the next video we'll go over that.